Recently, several exploits were published for CUPS, the formerly known Common Unix Printing System or services. And I think the best way to understand these and to mitigate the risk from them is to actually see a step-by-step guide of how to use these exploits to actually compromise a real system. And so first up here, I've got a diagram to help out along the way. We're going to look at the very first step here, which is a phony printer announcement. You could imagine screaming at the top of your lungs, "Hey, I'm a new printer," and everybody nearby that keeps track of printers might take note, ask you for some details, and then store information about how to use you in the future. That way, when users go to print, the printer is right there. They don't have to set anything up. So the first step is to create a phony announcement and to send that. So that's going to be from the fake printer. And that will be sent then to a CUP server. The CUP server is listening here for new printer announcements. That way it can register those printers so users can use them on that machine. And so we'll see first off how to send this fake announcement, and then we'll continue on hereafter with the other steps of the exploit. So the easiest way to get started here is probably just to create a UDP packet and throw it at the CUP server and see what happens. So I'm going to do two things here. On the bottom, this is the CUP server. It's called victim. Down here, I'm going to grab the logs for the CUPS browsed service, which is a service that listens for these announcements. So down below, I'll have the logs here. I'll clear that out though so we can see new entries. And then up above here, I'm going to jump onto the fake printer machine. And in this case, I'm going to use the nc command. Basically, I'm going to create a packet here with 0 and then the URL of my fake printer server. This is going to be the callback URL where the CUP service can get details about the printer, like the name, the make, the model. So we'll create a UDP packet here, send it to the victim machine on port 631. So if all goes well down below, we should get some log output from the victim. So I'll run that. There you go. You can see I get some logs down below. And if I were to scroll through here, you can basically see up at the very top, it's attempting to browse for data about the printer. And here's information about the remote host it's parsed, for example, the IP address, and the remote queue name, which is whatever here, which is exactly what I had up in my message up above. And then as you scroll through the output here, you're ultimately going to see that getting the printer failed because the call to get the printer attributes, which is going to use this URL up here, that failed obviously because I don't have a server listening there. So the next step here is to create a fake server that will receive the response for printer attributes that comes from CUPS. It'll then respond with fake attributes as well as an injection attack inside of the attributes. So it'll send that back then, the printer will then be added, and we'll come back to the rest of this in a moment. So for this example, I've got a Python script here, and down at the bottom of this, I'm basically going to send the UDP packet, but I'll do that after I start up a web server here. So here's the web server starting. The server that is spun up here is just a basic HTTP server. It'll run in a background thread. That way it's ready by the time we send the packet. The CUPS service will call back to this server, and I have a handler here. If I unfold this here, there's a do post method here, which handles post requests, which that's all we'll be working with. So the CUPS browsed service makes a post request. It provides an IPP request here. And then I'll turn right around. I'll build up a fake list of attributes. I'll inject some malicious attributes as well. And then I will respond with an IPP response. IPP is the protocol that's involved here. And so then I'll write that out. And then back in the diagram here. So once I respond with the attributes, those are sent back then to the CUPS server again. It then processes those. It takes the IPP attributes I sent, turns them into what's known as a PPT file, which you could think of as a driver for printing to a given printer. Assuming that goes well, then the printer will be added, it'll be available then, and we just have to wait then for a user to print. So let's do the next step here, which is to get the fake IPP attributes. All right, so to do that, I just have to spin up my Python server here. And then down below, I'll clear the logs here so we can see if there's any new logs. Just to confirm over on the right here, I'll run the lp stat command to show you there are no printers right now. And so now up above here, when I run my Python server, the packet's sent, the server started up. So here is processing the post request that came from CUPS browsed. And if I scroll through the output of CUPS browsed down here, at some point you're going to notice, and I have this turned on to a debug mode right now. I'll show you what that looks like. If I cut out the contents of cupsbrowsed.conf file, if I dump this out here over on the right. So I set debug logging for CUPS browsed to standard error. That way it's captured by the logs here. So once I do that, then I get output like I have right here with the attributes that are discovered. For example, here's the printer state, here's the printer name. Here is the printer more info attribute. This is what I use to inject the exploit. You can see additional payload here with foomatic rip command line. and cups filter 2. So where did those come from? Well, if I come over to my Python code here, if I take a look at not just the printer attributes that are fake, I also go into this method here where I inject extra foomatic arguments. If I expand this out here, just a list of a single attribute. Here is the printer more info, just like we saw at the command line. Expand that out here. This is supposed to be a URL, basically. So in this case, I just pass google.com, but then I inject an extra double quote in here. After that, I inject an additional 2 lines, basically, that are embedded inside of this attribute. And so this exploit takes advantage of the fact that attributes were not validated for double quotes. And so this is how I'm able to basically add extra attributes and package them up inside of what should be a safe attribute, but in fact is not. Of course, this is a command line call that I can use, so I'll pass a command here. We'll come back to that in a minute. All of that gets bundled up in the response. And then just to confirm this was actually received, in addition to seeing it in the logs here, let's make sure it actually gets into the PPD file. So I'll kill that off here. We'll come back to that in a moment. I'm going to dump out the contents of Etsy cups PPD. And I'll try to dump out this PPD file, but I don't have access as a lowly user, so I will elevate permissions here. All right, I have access now. And inside of here, if I look for Foomatic, there you go. So the more printer info gets mapped to this AP supplies. So the IPP attributes are slightly different from what actually goes into, you could think of as a PPD attribute. So printer more info goes to AP supplies. And then because I put google.com in there with that double quote on the end, I was able to break a line then and add additional, if you will, PPD attributes, one of which is to be able to run arbitrary command line calls here with the foomatic rip command line. So here's the command that I passed along. And then this cups filter 2 makes the magic happen by calling out to foomatic, which then grabs the foomatic command line and runs it. So now when the user sends a print from the server to this fake printer, the PPD will be used. Theoretically, it would transform whatever they want to print into a compatible format for our printer, kind of like a printer driver. And then in this case, we're also going to execute this remote compromise. So over in the diagram, we got to this part right here. We've added the printer. In fact, we could confirm that over the command line here over on the right. I'll run an LP stat again. You can see there's the fake printer. That's the IP address of it as the name. So we've got the fake printer. Now we're just waiting. Eventually, the user triggers a print to it. That'll execute our command, and then that should phone home. So that's the last part, which is what exactly do we run for a command? If I come over to my server Pi again. So several different commands. I dump out who am I echo out some file information, take all of that output and I curl it, and I phone home basically back to the same server, attach the output to the body of the post request. So if all goes well, we should see some logs here up above. I clear this out. If I clear this out down below here, we can take a look at printing as well if we want. Over in the right here, I can use the LP command to trigger a print. I can just print echo foo, send that off with the LP command to my new printer. That's just like a user triggering a print. All right, so here we go. I'll trigger that print and take a look at that. Up above here on our attacker server, you can see a request to post/phone/home. So theoretically, we should have the payload, and yep, here you go. Here's the body of the request there, the post request, which means that we successfully exploited this remote machine on the victim. Some code ran. The output of it then was sent off to the attacker server. And if you look at the output here, the very first part of the output is LP, and that comes from the first command I run is who am I? That way we can see which user this is running as. Thankfully, it's not root, but the LP user could have access to some sensitive things. I then pipe out some delimiters here. I read one of the files here, that PPD file, which a moment ago I showed you that was protected, that you had to have elevated permissions to access. Well, I perform a word count on it to show you that I can access it. And here's the word count right here. So actually, if I take that file real quick here, I try to run this as a lowly user here. You can see I don't have access. If, however, I change this to root, there you go. Now I have access, and 103 is the count of lines, and that matches right here with 103. All right, the next part here is a listing of files inside of that directory. So essentially, list out the files here. And I think I did an ls-al. There you go. There's the file. Let's copy this line right here. See if we can find that up above. There you go. So I have the listing of files. And I did this just to confirm. You can see here that not anyone has access to even read the file. Of course, you could imagine I could have grabbed the Etsy password file. Maybe if I had access to the Etsy shadow file, I could send those. Or of course, I could access sensitive information, or I could download some script from the attacker server or somewhere else that could set up additional exploits. The sky's the limit at this point in time. I guess the only limit is whatever the LP user can do in terms of permissions. Of course, by now there are patches for this. So to be able to run through a demo in a new environment, I actually had to pin my package versions inside of Ubuntu so that I wouldn't grab the latest packages, which speaking of, I have a list of those actually. If you go out to my GitHub repo here called examples, inside of here, you'll find all the files that I'm using. I would strongly encourage you, if you think you have some servers on your own network that might be compromisable, go ahead and take this code and try it out. See if you can go step by step through the process. See if you can actually compromise your own servers. Please don't use this on other people's servers, but absolutely use it on your own to make sure you lock down those machines. And so inside of here, there is the Python servers code and servers folder. So there's the Python file, there's the diagram, and then I even have some notes here as I was going through the process of testing this out. And inside of those notes here, you can see I captured a list of the packages that I used. I also link up above here to the patches that were released to fix this. Here's the one for cups browse D. 10.1 has the patch, whereas I was using version 10. And then one last thing I'd like to say, why exactly is this happening? Well, I just want to take a moment and point out some of the code for this project. The first thing I want to say is this one file on the left here is for cups browse D. It's for the daemon. This file has 14,000 lines of code in it. And it's C code. It's not exactly straightforward to read this unless you work with C all the time. I should say there are a lot of good comments inside of this code base, but at the end of the day, it is C code, so much of the time is going to be spent on memory allocation, cleaning up memory, pointer logic, making sure you don't go past the end of the line, null terminators. And so you have to spend a lot of time skipping over the boilerplate code to try to figure out the meat of what the logic is it's actually executing. Or I guess you have to dig through that boilerplate if you want to find some compromises. For example, that there was not validation happening on these attributes. And that's just one of the files involved here. It also uses another file here. It actually uses several other files. This one's inside of libppd. So this is for PPD generation. And the function here is to create a PPD from an IPP. So IPP, that's the protocol that the attributes are initially sent back from the printer. Those are then turned into a PPD file. And so here's the logic for this. And I believe this function alone, I think, is 500 lines long, and it has lots of calls out to other functions. And again, it's the same thing. A lot of time is spent on parsing things, allocating memory, freeing memory, etc. So whenever you have a project like this that's written in a low-level language where a lot of work has to be put into making sure that you don't make a mistake in allocating memory, or you don't make a mistake in freeing up memory, well, in that case, there's going to be a ton of code that basically gets in the way of seeing what's actually going on, which can make it very difficult to spot bugs, very difficult to miss the fact that you're not validating an attribute. And so it's very difficult to secure at the end of the day. And of course, I'm left wondering, is printing a domain where we need performance at the expense of clarity in terms of the code? Do we really need to have the fastest code possible? Or would it be possible to rewrite a lot of this in a higher level language and cut out probably 2/3 or 80% of the code here so that we can focus on correctness, because performance is probably not actually an issue for most printing scenarios. All right, before I wrap up, I want to give credit where credit is due. This is the person that discovered the vulnerability. They provided a lovely write-up with lots of good steps in it to help me basically recreate or reproduce their exploit. I'd encourage you to check this out, read through it, give this person a follow, and then in the comments down below, let me know what you think of this. Is this something you find interesting? Would you like more videos like this? Let me know down below.